So, welcome everybody. My name is David Gregg. I'm from Trinity College, Dublin. This is joint work that I've done with my research group, particularly with Andrew Anderson, who's here. So, I'm going to be talking about a few different things. I'm particularly talking about doing convolution as found in convolutional neural networks and other types of neural networks using general matrix multiplication. And that's a pretty well-known strategy. And by far the best-known strategy for doing this is a method known as im to call, although im to call strictly is the operation that's done before the matrix multiplication. And there's an issue with im to call, which is that it needs quite a lot of memory. And we have come up with some improved ways of doing convolution that don't need as much memory, but still allow us to use gem. And I'm also going to say just a few words about when you've got a bunch of different approaches, how to select the good one. So if we think about multi-channel convolution, we've got an input image, we convolve it with a whole load of kernels. Both the input image and the kernels have a bunch of channels, and each of these kernels gives us a single channel output image, which are concatenated together to form a stack of, to form a new set of images which become the channels of the next layer. So im to call is kind of the classical gem-based convolution. If you read the early papers, they said, wow, we can get this really good speed up by converting our convolution operation from a loop nest into a matrix multiplication. And it's pretty widely used in deep learning frameworks. And it's based on a very old idea around creating a tuplets matrix. And it's a great method, except that it expands the input size by a factor of k squared, where k is the dimensions of your kernel. So if you're doing a 3x3 convolution, the size of the image, or the amount of temporary space you need is 3 squared times the original input. And that's quite a lot of space if you're working on an embedded device or a kind of memory-constrained device. Now, this issue isn't nearly as big a problem if you're doing a strided convolution. And if all our convolutions were strided, we wouldn't have to worry too much about this. But unfortunately, very, very few of our convolutions are strided. So this can, as you can imagine, be a big problem on embedded systems and also on any sort of system where you've caches and you're worried about memory traffic and the energy that's used by memory traffic. So how does im to call work? Well, you start off with your usual kernels, you've got your image, and the image gets replaced by what we call a patch matrix, and each of these patches is the dimensions of the k by k kernel, and we have w times h of them. So we end up with a piece of memory that's significantly larger than the original input. And then out of this, we finally get the result matrix as before. So we've got this issue with im to call is that it needs quite a lot of space, and if we're working on embedded systems, we don't really like things that take a lot of space. And so what we've been working on for some time is, could we find another algorithm that allows us to have all the goodness of gem, all the speed, all the ease of building the algorithm, but we don't have to build a patch matrix that uses all this space. And we propose a family of gem-based algorithms, and they're based on a different way of writing the convolution using gem. And they don't need a patch matrix, and they don't need a whole lot of extra memory. So if any of you have ever worked on vectorizing compilers, you will probably have tried to, or if you've ever written vectorized code for a simple 2D convolution on an image with a single channel, you'll probably have figured out at some point that actually the way to do 2D convolution is not to try and load 3 elements into a vector and things like this for a 3x3 convolution. The real way to do it is you take one element of the kernel and you multiply it by all the elements of the image. And then you take one element of the kernel and the next element of the kernel multiplied by all the elements of the image. So what we end up is, we've got this kernel here in this example with 3x3 kernel, and we're convolving the image. And the way that you do this, if you're writing it in vector code very commonly, is that you'll take the image and you'll produce 9 copies of the image, each multiplied by one element of the kernel. And that vectorizes very nicely, and people who've written the vectorized code will probably be very familiar with that. The problem is, of course, you can't just add these things up together. You can't just add all the matrices on top of each other, because relative to each other, they're all in the wrong place. But what you can do is you can say, well, okay, so I've got this top left matrix, which is the result of scaling the image by the top left pixel of the kernel. And if I take that and I just shift it over a bit, then all the elements will be in the right place. And similarly for each of the 9 elements, except for the middle one, which doesn't have to move. And that's a common way to vectorize convolution, just plain old convolution. And we were thinking, well, perhaps we could do something similar with multi-channel convolution with multiple kernels. And essentially what we did was we took our algorithm for scaling matrices and adding them together, and we replaced the, scaling a matrix by a scalar with scaling a matrix by a 1-by-1 kernel. So a 1-by-1 kernel, it sounds ridiculous to do 1-by-1 convolution, but of course, in DNN convolution, we have multiple channels, so a 1-by-1 convolution starts to make sense. So we replace the matrix scaling by 1-by-1 DNN convolution, and then we do k-squared of those convolutions, and then we need to add them up in the right order. And if we add them up in the right order, we'll get the right answer. And a very nice thing is that 1-by-1 DNN convolution is simply GEM. It's exactly the general matrix multiplication call. So no extra patch matrices are needed. Now, a downside of this approach is that we need to do more gem calls. So we have to do k-squared gem calls is one downside, and the other thing is we have to add them up in the right order, and that gets a little bit tricky. But we avoid using a whole load of extra space. So 1-by-1 DNN convolution, we've got a kernel that's of size 1, and so it's a very, very much simpler operation than more general matrix multiplication, or sorry, more general convolution, and it can be implemented with a single matrix multiplication. So my postdoc, Aravind Vasudevan, came up with what we call Aravin's accumulating algorithm. And we apply this exact approach where we do the 1-by-1 convolutions, we do the k-squared of them. We produce the k-squared output things, except these have multiple channels. And then we add them up in the correct way. And a way that we do this to avoid using lots of extra memory is that we just produce one of these output matrices at a time. So we need a temporary buffer that's the size of the original image, but not k-squared times the size of the original image. And so that's quite a nice saving. It's a factor of k-squared saving in extra space, which is very nice. Now, adding them up in the right way is a bit complicated because, of course, the things are in different places. The result matrices, the results of doing these 1-by-1 convolutions, the things appear in the wrong places relative to each other. So we need to do a little bit of we need to do post-pass shifting, what we call shifting and adding, where we kind of shift the matrices in memory and before we do the addition. Now, of course, we don't actually shift any matrices in memory. What we do is we do pointer arithmetic, but that allows us to kind of virtually shift the things in memory. And then we need to remember not to add certain things on because actually these things fall outside the boundaries of the correct answer. So we were pretty happy with that algorithm. And we thought we were doing great work. And then one of us had an idea, and they said, well, hold on. The GEM library, for those of you who know the GEM library, it doesn't just do matrix multiplication. It also does accumulation. It allows you to add a matrix onto a matrix. You can get a result matrix, and you add it onto another existing matrix. So why don't we do the accumulation like that? And it's potentially faster than doing a post-pass loop because we do it as part of the gem call, and so we don't need to take an extra pass over the memory. We don't need to pull a whole load of extra stuff into memory. It improves locality. There are all sorts of advantages. Actually, getting the algorithm to work is a little bit complicated, and there's a couple of complications. The first one is that we shift the result matrices when accumulating, and the gem call doesn't really have an option to shift the result matrices when accumulating. So we need to be very careful about how we do the pointer arithmetic to tell it where to write the data. There's another issue, which is that in all these, at least two-dimensional convolution algorithms, there's all sorts of special treatment of the edge pixels in the result and edge pixels in the input. And we have to deal correctly with these boundary pixels. Now, the GEM algorithm hasn't heard of boundary pixels. It doesn't know anything about them. All it knows is that it's doing matrix multiplication. So just to give you a little bit of a feeling for how we solved some of the things around accumulating into the right places, if you can see the the input kernels on the right. So we've got 3 by 3 kernels, each with C channels. And if you see each of the letters A, B, C, D, E, F, this is a picture of where we need to tell the GEM algorithm to start writing the matrix result. So we tell the GEM algorithm that the result matrix starts here for when we're computing the A matrix. It starts here for the B matrix, here for the C matrix, and so on. And for some of the ones, for the ones from the bottom row, we need to tell the GEM algorithm that to start writing before the start of the result matrix. And it took us quite a while, actually, to figure that out. We actually thought it was going to be the opposite way around. But if you do that, then everything gets written in the right place. And apart from a whole load of boundary pixels, which have completely wrong values, quite a lot of the result is correct. So, kind of okay, kind of right is pretty good. So the next problem was, of course, that we were, how do we deal with these edge pixels to get the right answer? Because, of course, convolutions, they stop at the edge of the image. And we're building our 1-by-1 convolutions out of GEM. And we're kind of using GEM for a purpose it was never intended for. It's not intended for doing convolutions. We're telling it to, plonk down results in the middle of a matrix or before the start of a matrix that we're actually intent to write to. So all the boundaries, we spill over into the next row of the result. And so we get kind of garbage, and we get lots of wrong values in the result matrix. So we had a couple of strategies that we tried to solve this. One of them was to try and fix up the values in a postpass, and we found that was very, very inefficient. It had very, very poor locality. It was reasonably expensive, but it had terrible locality. So that strategy didn't work very well. And the other strategy we came up with was, well, maybe if we modify the input matrix, we can get the right answer. We can get the right answer to come out that we want to deal correctly with the boundaries. And so we carefully place zeros. And this is what I think of as a guillotine algorithm. Effectively, this is our original image. So say we were doing the convolution for this 1-by-1 kernel. We need to take the original image and we chop off the rightmost and bottommost part of the original image, row of the original image. Now, we can't actually eliminate these things because GEM has certain requirements. It requires that the data is laid out in a certain order in memory. We can't chop the parts off it easily. But what we can do is we can fill these with zeros. And so as we do our computation, we take parts of the image, we fill them in with zeros, and then we recover them. And this will finally give us our correct answer. So looking at the kind of space complexity of the algorithms, M2call requires one GEM call, and it does k-squared CHWM, so that's the number of channels, the height of the image, the width of the image, and the number of kernels. And the extra space is quite large. And then for some of the other algorithms, the extra space becomes smaller. And actually, we need plus W plus H as well. It just struck me onto this, but it's not a big additional factor. Okay, so we did some experiments and we tried this out on an ARM Cortex A57 and an Intel Core i5 4570. The work that we're doing is specifically aimed at inference on small systems, so we used a mini batch size of 1. Now you might see, we're going to show some comparisons with some other libraries, and the comparisons for them won't necessarily look fantastic, but I think what you should bear in mind is that a lot of those libraries are not really designed for a batch size equal to 1. So you shouldn't think really badly of them if they don't do all that well in some cases. Actually, in the initial case, we're not going to show them. So we've got multiple implementations of each method. So a problem that we have when we're doing this work is that we're comparing different convolution algorithms, and all of them have the same complexity, time complexity. And it's, small variations in how you implement these algorithms can make a big difference to an execution time. And when I say big, I mean, 10, 15, 20, 25% difference in execution time. And so it's very easy to compare 3 different algorithms and to get the opposite results just by doing slightly different tweaks. So what we did was we implemented a bunch of different variants. We had a summer intern who was very, very good and very enthusiastic, and he implemented a bunch of different variants. For him to call, we implemented 23 different variants. It seems ridiculous there'd be so many, but actually they fall out quite naturally. And we went with the fastest variant in each category. So in this one, we took a row major layout. Rather than copying all the data from the original image, we copy some of the data from the patch matrix as we build it, and that improves the locality. And then for Argvin's accumulating algorithm, we did a row major strategy, and then for the gem accumulating algorithm, we did row major, and we called gem with A not transposed and B transposed. So what sort of results did we get from this? So here are some results in the Core i5. What we see is that, in general, Argvin's algorithm doesn't do brilliantly. Im2col is a very good algorithm. It does well across a wide variety of things. And gem accumulating is perhaps a little bit worse in a lot of cases, but there's not much in it. If we go to multicore, we see sometimes gem accumulating does a bit better, sometimes it does a bit worse. If we look at the Cortex A57, again, we see gem accumulating doing a little bit worse, sometimes a little bit better. And if we look at the ARM multicore, we tend to see gem accumulating doing well. And we think that this is because the kind of cache sizes and things like that on the ARM processor are relatively small compared to the Intel processor. And so we start to see a bigger win from using less memory, particularly on the Cortex A57. And if we look at the extra memory required, we see kind of orders of magnitude in differences in the amount of memory that's needed. So very, very large differences. We probably need to add a small additional factor into these. Now that I think of it, we didn't take it into account. But we see very, very large differences in the amount of memory used. Okay, so what would I say about that work? Well, DNN convolution can leverage optimized gem libraries, as everybody knows. Im2col is a great algorithm. It's a fast algorithm. It's really good, but it does need an awful lot of space. And our gem accumulating approach, it offers kind of similar performance, sometimes a little worse, sometimes a little better, but it really requires a tiny fraction of the additional space. So we're quite happy with that. So if we just have a very short moment, I might just talk about one or two other things. So we've got a paper on this on arXiv, and we're releasing our code shortly, if anybody's interested. In the process of doing this, we implemented a bunch of different convolution algorithms. And what we found was that there's kind of different major classes of convolution algorithms. And we thought, well, how do you choose which one to use? So we've got a simple loop nest, which tends to be good for memory size, but it's really hard to write it to be efficient. We've got the Im2col, which is good, and it's good all-rounder algorithm, great for stride, it's terrible for memory size. We've our accumulating algorithm, great for memory size, not so great for strided. There's a MEC algorithm, memory efficient convolution, very interesting algorithm. The results in the paper on MEC show that it absolutely, it defeats every other algorithm in sight. No other algorithm can compete with it. We weren't able to reproduce that result in our experiments, and we found that actually in our implementation, the execution time is very poor, and it used a lot of memory, but maybe we're missing something. And then there's FFT convolution and Vinograd convolution. So there's many of these algorithms that have been proposed and are used. And we have a library of about 70 different convolutions, different variants of the algorithms. And we had this question, if we've got a whole bunch of implementations, how do we pick which is a good one to use? And in particular, we don't use the same memory formats, the same data sizes, the same memory layouts for different algorithms. We tend to pick ones that work well for that algorithm. So, well, if you want to get different implementations to work together, even if they're working in different formats, we have a legalization pass, and we can insert format conversions and things like this to fix those problems. But of course, those format conversions take time, and sometimes we need a chain of conversions. Maybe there isn't a direct conversion between these two different types. So we were wondering, given that we've got some algorithms are good for some things and not for others, what can we do about this? Is there some way we can select between them? And what we do is we profile each of the individual layers individually, but we find the right combination of different algorithms analytically. And we use a classical problem that's used in compilers, partitioned Boolean quadratic programming. And it's a classical optimization problem. It's used for It can be used for register allocation, for instruction selection, for address mode selection, and things like this. And what it allows you to do is it allows you to attach a cost to the different choices for different algorithms for each layer of a neural network. But it also allows you to attach a cost to the combinations. So we've got 3 choices here, 4 choices here, and these are the 12 choices of combinations. And so, for example, in this case, there's no transformation that'll bring you from one layout to the other. And what we saw from this is, here's just some very quick results. We only have them on Intel at the moment. Actually, Andrew has ARM results downstairs. But what we see is that if we look at different things, we see a simple direct algorithm. That doesn't really work terribly well. We've got IM2 and Kern2, which is our gem accumulating approaches, work reasonably well. The Kern2 works reasonably, Then we've got Vinograd and FFT. But what we see is that if we take the combination of these two, chosen with the PBQP algorithm, we can select the really best implementation for each layer and get very nice speedups. And we see similar things using multiple cores. And we get very, very nice speedups. So what would you say? Key takeaways in this. There are lots of ways to do convolution. There's no one best way to do it. Some algorithms are only good in special cases, but you can get significant speedups from choosing the right one. In general, compilers are great. People should use compilers more. All these optimizations that we've developed for various purposes can be applied to all sorts of things, including neural networks. Okay, so thank you.